Boy, oh boy, we are coming right down to it. March we onward. Lesson 27 is the first one that deliberately looks at the other question that the calculus tries to answer. The calculus tries to answer two main questions. One is, how do you find the slope of something that is curvy? How do you take curvy things and make them straight? That's one of the questions that the calculus deals with. The other question that the calculus deals with is, how do you find the area of something that's curvy? And not curvy like it's a circle, but curvy like it's curvy. How do you find the area of something that's curvy? And that's what we devote ourselves to for the foreseeable future. Um, if I can, here's the area problem. So you have some function and you're interested in some interval from maybe a to b. What you're interested in is this area. How big is this area? And so you look online for the area of a weird blob and you don't find anything. But you do know from when you were a kid that you know how to find the area of a rectangle. And so basically, we take this interval, we break it up into a bunch of small subintervals, and then we build rectangles out of those subintervals. We add up their areas, and we figure that's good enough. That's good enough. So we would take this interval, we would break it up into a bunch of sub-intervals, and then we would build rectangles whose heights are based maybe on the left endpoint of each little sub-interval. On the left endpoint of each little sub-interval, we just run the left endpoint up to the curve, and you figure, well, the areas of the red rectangles added all together, that's close. That's close. But then some of you are going to say, no, 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 that's not close enough. Maybe if we use the right endpoint, things will go better. Maybe if we use the right endpoint. And the truth is, sometimes the left endpoint is going to be better, and sometimes the right endpoint is going to be better. And sometimes we don't want to use either of those, but whatever is convenient will work. Maybe the right endpoints go better. Now, in truth, neither of these give you the actual area, but they give you an approximation to the area, and that's a good place to start. I'm going to demonstrate in the following way. This is x squared plus 2 on the interval from 0 to 2. Interested in this area in here. This area, the area bounded above by x squared plus 2, bounded below by the x-axis, and bounded on either side by x equals 0 or x equals 2. And I'd like to do two different approximations. I'd like to do a left endpoint approximation with 4 subintervals, and I'd like to do a right endpoint approximation with 4 subintervals. So if we do a left endpoint approximation with 4 subintervals, well, we need 4 subintervals. Well, that splits things in half, and that splits things in 4 pieces. So we take our interval, break it up into that many equal pieces, and then we build the rectangles. We build the rectangles where the height is the left endpoint. The height is determined by the left endpoint. So what does that mean? Well, the areas of each of these rectangles are 1/2 times the height. 1/2 times the height, 1/2 times the height, 1/2 times the height. So the heights are f of 0, f of 0.5, f of 1, f of 1.5. We take those 4 left endpoints, substitute in here, 0 squared plus 2, 0.5 squared plus 2, 1 squared plus 2, 1.5 squared plus 2. And this turns out to be 5.75. Now, you and I both know, just by looking at the picture, that 5.75 is a little small. The actual area is bigger than 5.75. Well, what if we try a right endpoint? A right endpoint approximation with 4 subintervals. So we take the right endpoints and we let the right endpoints dictate the heights of the rectangles. The right endpoints, because this function is increasing, are going to generate too much area, but it will still give us an approximation. The areas of each of these rectangles are 1/2 times the height. 1/2 times the height, 1/2 times the height, 1/2 times the height. How do you figure each of the heights? You take these 4 right endpoints and figure out function values there. So 0.5 squared plus 2, 1 squared plus 2, 1.5 squared plus 2, 2 squared plus 2, and this turns out to be 7.75. Now, you and I know that this is too big. There's all this extra area here, but it is an approximation. To be clear, we call this is called a lower sum because on each subinterval, we took the lowest possible y value. This is called an upper sum because on each subinterval, we took the largest possible y value. We took the largest possible y value on this subinterval and made a rectangle. We took the largest possible y value on this subinterval and made a rectangle. We took the largest possible y value, made a rectangle. So this is a lower sum. This is an upper sum. The actual area is in between those. So let's approximate the area with L9 and R9, meaning we're going to approximate the area with 9 little subintervals. Here's the function. 10 over x. 10 over x from x equals 1 to x equals 10. X equals 1 to x equals 10. So if we're going to use 9 little subintervals, well, I'm imagining 2, 3, 4, 5, 6, 7, 8. There's 9 little subintervals. So what is the left endpoint approximation going to mean? It means we let the left endpoints drive the heights of the rectangles. We let the left endpoints drive the heights of the rectangles. The widths of each of them are 1. And the heights are determined by function value at 1, function value at 2, function value at 3. So the function value at 1, the function value at 2, and so on, the function value at 9. You should take a moment right now and figure out what this is. This will be an upper sum because on each subinterval, the left endpoint's the highest point on the interval. So it's an upper sum. And then you should figure out what happens if you use a right approximation. If you use a right approximation, what happens to your rectangles? Each of the rectangles has a width of 1. but the right endpoint determines, the right endpoint determines, the right endpoint determines. You should take a moment and figure out what these are. So really, hit pause, figure out what they are. Okay, so this is about 28.290, and this is about 19.290. You should figure that for you should make sure that you have those answers. You should. And then when you're looking to practice, because you want to approximate the area under y equals x cubed minus 3x squared plus 3x plus 2 on the interval from 0 to 3. Use an L6 and an R6. Hint here, the actual area is 12.75. So your L6 should be just less than that, and your R6 should be just more than that. So let me set you up for the big idea that's coming. The big idea that's coming is this idea of a Riemann sum. And that's what happens when all of the subintervals have the same length, like all of the ones we've done so far. If all of the subintervals are the same length, then you get a Riemann sum. It is of the form summation as I goes from 1 to n of f of x sub I star times delta x sub I. The f of x sub I star is the value of the function at any point between x sub I minus 1 and x sub I. So any point you like. Could be the left end point, could be the right end point, could be the midpoint, could be the point 2/3 of the way, could be your favorite number, doesn't matter. X sub I star is your favorite point between x sub I minus 1 and x sub I. All of the delta x's are the same for all of the subintervals. And then we sum them up. We add up the areas of all of the rectangles. So the area under the curve is given by, well, guess how this works. You take the sum of, you take this Riemann sum thing, right? You take a bunch of heights times the bunch of widths, you add them all up, and then you play this game where you let the number of rectangles get bigger and bigger and bigger. Why? 9 rectangles is great, but 18 would give us a better number, right? Because they'd be thinner and we could fit more in and there'd be less of this stuff sticking out over here. We'd get better approximations. And 18 would be great, but 36 would be magnificent. Less of this extra stuff. So if we could take the number of rectangles to infinity, that would be the most amazing thing, period. And so that's how we define the area under the curve. Now, there are all sorts of beautiful connections for us to make, but that'll have to happen in class. All right, we'll see you there.